Hello everyone, this is our oral presentation for CVPR 2024. I'm Mingyuan Meng, the author and the presenter for the paper titled Correlation-Aware Coarse-to-fine MLPs for Deformable Medical Image Registration. I'm so honored to have this opportunity to present at this stage of CVPR 2024. The author of this paper also includes Dagan, Feng, Leibi, and Jinman. We are from the School of Computer Science, University of Sydney, Australia, and the Institute of Translational Medicine, Shanghai University in China. Our study focused on deformable medical image registration. Image registration funds a spatial transformation between a pair of fixed and moving images, through which the moving image can be warped to spatially align with the fixed image. Typically, a fine registration is firstly performed to eliminate the linear and large spatial misalignments between the two images. Then, deformable registration is performed to reduce the local long-range deformation, which is the most challenging step and is the main risk focus for medical image registration. The image below provides the examples of two brain MRI images to be registered. It can be seen that after a fine registration and deformable registration, the moving images become spatially aligned with the fixed image, both locally and globally. Here are the literature reviews for our risk problem. I will first review the vision backbone used for deformable registration, from CNN to transformer. The early method, like the widely used voxel morph, adopt CNN as its backbone, as exemplified in the left figure. They usually adopted a UNet-like encoder-decoder architecture to realize a direct mapping from image pairs to spatial transformation. The later registration method, like the recently proposed transmorph, adopted the transformer as its backbone for its capability to model long-range dependency to handle large deformation between images. However, it should be noticed that transformers were used after downsampling via patch embedding, which means the transformer cannot directly process a high-resolution image feature that contains the detailed anatomical information. Even though the current transformer-based method still achieved better performance than CNN-based method, which set the state-of-the-art performance. Then, let's review the network architecture used for deformable registration, from the simple direct registration architecture to progressive coarse-to-fine registration architecture. The direct registration architecture tends to use a simple UNet-like network to directly model the large deformation. However, the progressive registration architecture performs multiple steps of coarse-to-fine registration, which decouple the large deformation into multiple small deformation. This can be achieved by mainly two types of method. Iterative coarse-to-fine method use cascaded networks or run a single network with multiple iterations to perform the multiple registration steps. However, this kind of method inevitably incurs heavy loads of computation and GPU memory due to repeatedly running the network. Recently, non-iterative coarse-to-fine method was proposed, which perform multiple registration steps by running a single parameter network for a single iteration, such as the recently proposed NiceNet, NiceTrans, and Model T. Now, I will briefly discuss the vision backbone based on multilayer perceptron, or MLPs. MLPs can capture long-range dependence without relying on self-attention operation, showing advantages over transformers on computation and memory consumption, as exemplified in the figures below. Compared to the popular vision transformer, or VIT, that employs the expensive multi-head self-attention operations to model the global relevance, the MLP-based MLP mixer uses the simple density collector layer to model the global relevance along the spatial and channel dimension separately, which saves a lot of computation. Recently, we found that MLPs can process high-resolution image feature maps to capture fine-grained long-range dependence at full resolution, which is crucial for the medical image dense prediction task, including segmentation, registration, and restoration. The relevant evidence can be found in our recent empirical study titled Full Resolution MLPs Empower Medical Dense Prediction, which is currently available at Archive. Then I will discuss the key limitation of existing method. Existing transformer-based registration method achieved the state-of-the-art performance by leveraging the transformer's capability in modeling long-range dependency to handle large deformation. However, transformer cannot directly process the high-resolution feature map that contains the crucial detailed anatomical information in medical images. Typically, transformers were employed after downsampling via patch embedding with a window size of at least 4x4. For example, in swing voxel morpho, the high-resolution feature map at the full and halved image resolution were directly overlooked. In transmorph, the high-resolution feature maps were still processed by CNN, which means that the fine-grained long-range dependency at high resolution still cannot be captured. This limits the registration performance as deformable registration required processed dense correspondence between each image pixel. MLP is more efficient than transformer by removing the self-attention operation, which provides the feasibility of modeling fine-grained long-range dependency at high resolution. This motivated us to introduce MLP into registration problem. Despite that MLP seems promising for deformable medical image registration, they have not been extensively explored for this problem and lacks consideration of crucial inductive bias. Specifically, existing MLP-based models tend to simply stack MLP block as a feature extraction encoder and has not been optimized in the state-of-the-art Coarse-to-fine architecture to realize the progressive medical image registration. Furthermore, existing MLP blocks tend to mix spatial information globally and are insensitive for local range dependence. However, medical images usually carried both large and small local deformation. For example, in the right figures of 4-brain MRI imaging, both large and small local deformation exist and are highlighted in the red and blue boxes. Also, existing MLP blocks did not explicitly model the local correlation between features. However, there have been studies showing that the local correlation between feature maps can provide important spatial guidance to improve the registration performance. Motivated by the previously discussed limitations, we introduced MLP to the deformable registration problem and proposed Coral MLP, a correlation-aware Coarse-to-fine MLP-based network. This network has a CNN-based hierarchical encoder to extract two feature parameters from the fixed and moving images separately, followed by a correlation-aware Coarse-to-fine registration decoder based on our new CMW MLP blocks. The decoder takes the two feature parameters as input and then performs 4 steps of Coarse-to-fine registration. One deformation field was produced at each registration step and then was used to warp the feature maps of the moving image, which were further used to refine the deformation field at the next registration step. The whole network used a level correlation-aware Coarse-to-fine registration architecture that considers both image level and step level correlations. There are 2 MLP blocks used beginning from the second registration step. The first MLP blocks considered the image level correlation between the feature maps of the moving image and the fixed image, while the second MLP blocks considers the step level correlation between the former and the current registration step. Then I will introduce the key component of our network, CMW-MLP, which means Correlation-Aware Multi-Window MLP block. This block was designed as a general network block that takes 2 sets of feature maps and can explore the potential correspondence between them. Specifically, there is a 3D correlation layer used to calculate the local correlation between the 2 input feature maps, followed by a multi-window MLT module to capture correlation-aware multi-range dependence. Within the multi-window MLP module, there are multiple window-based GMLP branches to capture both large and small local deformation existing among the medical images. Empirically, we said there are 3 GMLP branches with a window size of 3x3, 5x5, and 7x7, which allowed us to achieve the best result in the experiment. In summary, the technical contribution of our study are threefold. Firstly, we investigate in leveraging MLPs for deformable medical image registration and propose the core MLP model. To the best of our knowledge, this is the first MLP-based coarse-to-fine registration network. Secondly, we propose the CMW-MLP block, a MLP block specifically optimized for deformable registration to capture correlation-aware multi-range dependence. Thirdly, we proposed a novel correlation-aware coarse-to-fine registration architecture, which considers both image-level and step-level correlations to provide enriched contextual information to guide each registration step. For experimental validation, we evaluated our core MLP with two well-benchmarked deformable image registration tasks involving a total of 7 public medical image datasets. The first task is the interpatient brain image registration. The training set includes more than 2,000 brain MR images acquired from 4 public datasets. The validation and testing were performed on 2 separate brain MRI datasets. The second task is intrapatient cardiac image registration. On the public ACDC dataset, the training and validation were performed on the official training set of the ACDC dataset, and the testing was performed on the official testing set. Table 1 and Table 2 presents the quantitative comparison for brain and cardiac image registration. As shown in the two tables, our core MLP achieved significantly higher dice metrics than all compared method, including the state-of-the-art transformer-based direct or coarse-to-fine registration method. It also should be noted that our core MLP achieved better registration accuracy without sacrificing the transformation smoothness, which is indicated by the matrix of lactive Jacobian determinators. We also can observe that the runtime of core MLP is similar to the existing deep registration method, or allowing real-time registration by using GPUs. Table 3 presents an ablation analysis on architecture designs. We first established a MLP-based direct registration model named MLP Morph as a baseline. By using MLP block in unit-style architecture, the baseline MLP morph have outperformed the CNN-based voxel morph and the transformer-based transmorph by a large margin, demonstrating the superiority of MLPs on deformable image registration. MLPs can capture fine-grained long-range dependence at high-resolution features, which is crucial for finding precise dense correspondence. Then, by employing MLP's blocks in our correlation-aware coarse-to-fine architecture, our core MLP outperformed the MLP morph by a large margin. This demonstrated the effectiveness of the proposed correlation-aware coarse-to-fine architecture. To further validate this, we separately removed either image-level or step-level correlation information and found that both of them degraded the registration performance. This further validated that both the image-level and step-level correlation information can help the registration process. Table 4 presents an ablation analysis on MLP blocks. We replaced the proposed CMW MLP block with 5 different existing MLP blocks and found that all these replacements resulted in lower registration accuracy, showing the effectiveness of the proposed MLP block. We attribute the improvement to 2 reasons. The one is the use of correlation information, and the other is the use of the multi-window MLP design. To further validate this, we established a degraded baseline MLP block by removing the correlation layer, which is named as the MW MLP. Even when the correlation layer was removed, the baseline MLP block still outperformed the 5 existing MLP blocks, implying that our multi-window MLP design is beneficial for deformable registration. We also found that removing either MLP branch will degrade the registration performance, and no further improvement can be observed by adding an extra MLP branch with larger window size like 9x9. They suggest that a 7x7 MLP branch have been sufficient to capture the large deformation in the deformable registration problem, while the 3x3 and 5x5 MLP branches are crucial to capture the small subtle deformation. Here are the conclusions. In this study, we have shown the effectiveness of MLPs for deformable medical image registration by developing the first MLP-based coarse-to-fine registration network. Our study suggests that MLP could be a superior alternative to popular transformer for its advantages on modeling fine-grained long-range dependency at full resolution. Since the proposed CMW MLP block is not strictly bounded to the proposed architecture, we also suggest that the proposed MLP block could serve as a general block applying to various network architecture for image registration tasks to leverage its capability to capture correlation-aware multi-range dependence among features. Thank you for your listening. Our code is publicly available at GitHub, and this work was supported in part by Australia Research Council.